Chip Erwin at Aeromarine, reporting here from Dayton, Ohio. Ben Bosma, my colleague, who just returned from Oshkosh Air Show with record numbers, record attendance, beautiful weather, and the first public introduction of our parallel hybrid system. And we had our own parallel hybrid pavilion in our tent in the show center. And I mention that because it's a big part of this program is commercialization, and we are verifying the market and reaching out and making contacts. And there's such a thing as a dead grass award. So many people walking around either an airplane or something innovative like our hybrid, and we certainly qualified for dead grass award. But the R&D center here is with Ben Bosma, where we work out of his shop for a lot of, and we queue up here for the air shows and so forth. And we were just reminiscing how far back we go, because I don't remember how many years I've been coming up here and working with Ben and AFRL. But now we dug around in some files, and it turns out around 2012 I started flying a Zigolo ultralight. And I go back into 1980. I've had so many engine outs. I probably had 3 or 4 of them at the Oshkosh Air Show alone, forced landings. The two-strokes simply tend to stop stroking. And that's the worst thing about ultralights. And at the time, some 12 years ago, I thought electric propulsion, which was just coming out, was perfect for ultralights, perfect for low energy aircraft like sailplanes and slower planes like the airplane I was flying. So I was an early adopter. I figured out how to get it to work and was the first one to fly into the Sun and Fun Air Show in around 2014. And around the same time, because I had been doing this R&D and was one of the early pioneers in actually flying electric aircraft, the CAFE Symposium, or the CAFE Foundation, put on a symposium in San Francisco, Silicon Valley, and invited me as one of their main speakers. So I prepared a slide deck and went out to present this proposal in front of 600 scientists and university fellows and other aviators and other people involved in electric aviation. It was quite interesting for me. But I got a call from Ben. Ben said he's coming out to meet me. So how did that play out?
Well, I was interested in what you had to say, and I was particularly interested in how electric aircraft were coming around, because I was not a cynic about it, but I understand aircraft and physics. I've been in the business for a long time. And I was trying to find a way to increase the endurance of a particular platform and proposed a hybrid solution. Now there's 2 basic types of hybrid. There's the serial hybrid, which is what a lot of people do, which I liken to a diesel locomotive. There's an engine that's powered by gas or oil that's connected directly to a generator, which is then connected to a controller, and then it's connected to 1 or more electric motors to propel an aircraft. There are many points in that thing that are single points of failure. For example, if the generator quits, or the controller quits, or the anything, you run out of fuel, the aircraft is not going to continue to fly. So at the time, we had an early car that was a hybrid. And hybrid cars are different in that they are parallel. By that I mean that you can run the electric motor with the engine in concert. They're together. Typically for a hybrid car, the motor is used for economy and also for those moments when you need a surge of power. And at that time, nobody was thinking about a hybrid aircraft engine. But I knew that Chip was going to be briefing something like that. I had already filed for a patent on one. And by that time, I think it was there was enough confidence that we could actually build one. So the main impetus for me was power for takeoff and climb, and then the ability to get yourself out of a very dire situation would be an engine failure, particularly an engine failure on takeoff. So with a parallel hybrid, you have the option of being able to run the electric motor with the same performance as the internal combustion engine. And for example, the worst case would be having an engine failure as soon as you got off the ground. And if you didn't have enough room to land in front of you on the runway, you're left with very few options. Really, the only safe option, if you can call it safe, is to land straight ahead. With a parallel hybrid, you can thumb in electric power that you may or may not have had when you were taking off and power yourself back up on a crosswind, downwind base and land out of a normal pattern. In fact, if you have enough battery reserve, which is not the same as battery to fly continuously or cross country, but battery to get you out of those situations, you'd be able to get back into the radar pattern, or if you were, say, for example, in the weather, enough power and enough battery endurance to get you around the pattern, to get you back on an instrument approach to land safely. The ability to put a hybrid engine into an aircraft doesn't end with small general aviation aircraft. There's no reason why it can't be scaled up to turbines. And by that I mean turboprops or possibly turbojets, but they tend to be very reliable. However, turbines have the problem of being very sensitive to heat and density altitude. So if you have a low power turbine, say in the 100 horsepower class, which would be a UAS or a general aviation class aircraft, you want to be able to augment that power in hot, high situations, because electric motors tend not to be sensitive to either altitude or to a certain extent temperature, at least for short term. So you can flat rate a turbine engine to its power at STP, standard temperature and pressure, and then use electric motors to augment it. So there's a lot of reasons why a parallel hybrid is superior to a serial hybrid for aviation use.
Well, we didn't actually know that then completely. We learned a lot about how the additional benefits. What I learned in early 2012, somewhere around there, was that electric power was just wonderful. It was quiet, it was reliable, I could fly low, I didn't have to worry about much the two-stroke engine or maintenance of it, but the battery didn't last long. And then I went to the symposium where I was speaking at, and quite a few of the other speakers were talking about were experts and scientists in the battery energy fields. And they said back then, more than 10 years ago, that the battery energy density would increase at best 5, maybe 7% a year. And anything that was really significant breakthrough would take at least 5 more years to be on the market. That's what I realized, that Ben and I were basically thinking the same thing. We need to augment that power.
Now, as far as the power is concerned, how do you get the power to the propeller? So a parallel hybrid engine essentially is a dual engine situation. So you've got multi-engine capability depending on how many of these units you pair together. The real breakthrough, I think, was the fact that we incorporated a sprag clutch. And I hold here in my hand a sprag clutch. It's a very simple device. What it is that it moves in one direction but locks in the other. So if you put this thing on the output shaft of your internal combustion engine or your turbine engine, and you have a failure, including a complete lockup of that PTO, it will freewheel. And now your motor, which is attached to the same drivetrain, can take over moving the prop, turning the prop. And that was the patented feature of this. We have 2 of them, 2 patents that is. We have a method patent which covers any clutch in any configuration between the 2 prime movers. And then we have what's called an apparatus patent, which is the one for our actual engine. We are in the process of incorporating coaxial motors into the patent, which will have a priority date going all the way back to 2016, 18, over 8 years ago. And then, which will mean that we can incorporate the clutch or clutches in a coaxial situation instead of offset. And then we've just recently added multiple motors to that. Again, priority going back to 2016.
So I got up and my speech was right after my friend Boris Popoff, who started BRS, the Ballistic Recovery System. And he was saying how great it was to be able to save your life and float down slowly with a parachute. And he knew this was coming because the pilot's on the CG, the batteries on their weight have to be on the CG. Back then they would start on fire way too often. The last thing you want to do is float down slowly with your ass on fire. So I said, it used to be crash and burn, now you burn to crash.
Yeah.
So after my presentation, Ben walks up and says, I'm Ben Bosma from the AFRL. And I said, what's AFRL?
Well, at the time, I was one of the chief architects of a platform that we were developing for the Air Force Research Lab. I've since left there. It's been probably 6 years now since I've been there. And I've used that time productively to further develop this engine. We had one at Oshkosh, as Chip said, but we actually had 3 of them. One of them was sort of a test engine based on the 670cc Predator. We had one there that is the 61 horsepower, 45 kilowatt, water-cooled, fuel-injected, electronic fuel injection with ECI and all that stuff. That is also part of the Aeromarine new V-twin program that we have been able to augment with an electric motor. There's a lot of features of that airplane that we'd like to talk about. This is about hybrid engines, but there's some technological advances that this thing has that no other aircraft had there. For example, we have the ability to switch tanks very quickly, electronically. We had Starlink on board. We had a very advanced avionics system on a very small airplane in the LSA category from Aeromarine.
You probably have seen these slides in our editing, but this is from 2014, where actually I'm flying an electric aircraft, and I'm suggesting a hybrid aircraft, and another slide where it sketched one out. So that was at the beginning.
Yeah, that was a long time ago, and it's kind of surprising that nobody has developed a parallel hybrid aircraft engine by now, but better late than never.
And we'll be flying it very soon. And this was the intro for the video. Chip Erwin, Aeromarine, Ben Bosma, Hybrid Aerospace, signing off. Chip Erwin, Aeromarine, Oshkosh 2024, and we're continuing our video presentation of our research of the turbine side of our parallel hybrid research. And now we're with Heron Engines, one of our engineering partners, and they have a beautiful, beautiful turbine. And we're going to start right here, and you can talk about this.
Yeah, here we have the simplest form of a free turbine configuration, turboprop engine, or turbo shaft, if you will. So it is 130 horsepower, 88 pounds, and we implement dual fuel system. And excuse me 1 second.
That is the sound of freedom.
So we have a twin fuel system for redundancy. It is vetted and working mostly with Jet A or the heavy fuels like kerosene or diesel, if you will. In the case of the hybridization, you can, because it is a free turbine, it can handle very easily the loads because the gas generator reacts accordingly to the load. So if you load it with a big load, it can handle it, and you see just some change in temperature. The gas generator rotates about 75,000 RPM, and then we have the free turbine and the reduction gearbox here that we have the output shaft.
Right, and now we can take this output side
Exactly. There,
and we can reduce it, which is better for our prop speeds. And with our electric motor mounted with all these mounting points and our cock belt system that goes around the electric motor and tie that into the ECU, where we can then double the power for climbing to altitude with only a small battery, because then we'll turn off the electric motor. The gas engine is up in cold air, which it really loves, and it's at its peak horsepower then at altitude, and it's recharging.
We have a service ceiling of 28,000 feet.
Yes, 28,000 feet, and the electric motor doesn't have a service ceiling. It doesn't care, but then it turns off and turns into a generator and recharges that small battery pack, which provides then a stealth mode option at a later time in the flight. So how many of these are in production now and in testing?
At
the
this
test
moment,
stage?
we have 4 pre-production engines that we are flying with our airplanes, and we are setting up the production at this moment.
So that's perfect for our program, because we're both starting out, and this is already not only a working model, but a flying model. So we're in a phase 2. This could be easily installed in one of our test bed aircraft and proven all the parameters.
It is a huge benefit. It is the 88 pounds. It is light enough, so you can implement it easy everywhere. It is very compact. The size is not bigger like an electric motor itself.
No, the frontal area is very nice. These will be outside the cowling, but the frontal area is beautiful. That means we can have a very sleek, efficient fuselage, low drag, and we have a long endurance, long range.
Also for the exhaust pipes, we can have something specific manufactured for the application. It is very easy configurable.
Okay, that's great. Well, thank you for that introduction. And there'll be
very much for your time.
in our final report, we'll have the specifications of this turbine along with the proposed electric motor to match up with it. Thank you, Alex.
Thank you very much.
Chip Erwin, Aeromarine, at the Hybrid Pavilion, where we're displaying the Redline turbine and some of the other hybrid technology that we're developing under this Phase 1 SIBR, and we're also parallel with the SIBR, we're commercializing these and developing these in real time, real working models, and showing it at the biggest air show in the world. And we'll show you the whole booth shortly, but let's get right into it with Brian from Redline and Ben Bosma from Aeromarine and Parallel and Hybrid Aerospace, our technology partners. So here we go with the Redline turbine.
My name is Brian Seegers. I'm a partner at Redline, and we're here working with Hybrid Aerospace and Aeromarine. We have a 100 horsepower recuperated free turbine turboprop. We call it a miniature version of the ET6, and it was developed originally for drones. And what we have here is basically the complete engine from prop flange to the inlet. The entire weight of this engine with accessories, perhaps 75 pounds. This one is currently fitted with an electric controllable pitch propeller. However, one of the reasons we're here on display is we're working with Ben at Hybrid Aerospace and Aeromarine to adapt 100 horsepower horsepower, perhaps 90 to 100 horsepower hybrid system, similar to what is being tested on the recip engines. And would you like to chime in here, or?
Yeah, I'm Ben Bosma from Hybrid Aerospace, and what we're doing here is we're exploiting and finally getting to use several patents that are part of Hybrid Aerospace to develop a parallel hybrid engine, which is unlike anything else here, which is typically people will call a hybrid something where they attach a generator to a motor and call that a hybrid. That's not a true hybrid. So our parallel hybrid technology is identical to what you would see in the automotive industry, the Prius, for example, or the Ford hybrid. I have an example of how that works over here, which would simplify it. So this engine right here is a very easy to purchase Harbor Freight Predator 670cc engine. It produces about 22 horsepower.
And available off the shelf for $950 with a free flashlight. $50 off on Father's Day.
That's right. So what's different about it is we have a redrive, which is a reduction drive that reduces the output RPM to a more reasonable RPM for swinging a propeller. I don't have it tightened up right now, but down here is a what's called a sprag clutch, sometimes called an overrunning clutch, and I've got one here that I've opened up, and what it does is it turns freely in one direction, but it locks in the other. There's no ratcheting, but that's how it works, and it fits right here. So as this engine turns in this direction, it grabs the clutch, but if you go in the other direction, that is as if I have the power coming from the other side, it freewheels. This allows the motor to power the propeller instead of the engine. However, because of this arrangement, we can actually do both. So if we had to, we could combine the output power of the engine with the output power of the motor to, in this case, double the power of the entire system. We're doing the same thing with the Redline turbine. We will have a motor connected to the output shaft of the turbine, and the two will combine, or the motor will be able to power it separately, or the turbine. Over here...
Well, Ben, if I may, this is a 3-month phase 1, which normally is just a feasibility study, but we've actually finished this, and both the motor and the engine have been running. And when we get back from the show, we will finish the installation of the integration of both of them, where we can use this test bed and use a scale to measure the thrust of the electric motor, measure the thrust of the gas motor, and then measure the thrust of the combined with both of them operating. And then that will be our first truly functional finished hybrid, parallel hybrid. But as you can see, when we're moving forward, and you can see a couple other engines here, motors, we can choose any gas engine, nearly any, and we can match it with equivalent power in kilowatts of the electric motor.
So
and then we just mill these rings that fit on with, there's other parts that aren't here, but you get the idea of how that would attach. So the next size up is the 60 horsepower V-twin, which we use on the Merlin light sport class aircraft, and we have that on display, and we'll be that's a brand new aircraft, and maybe take a quick shot of that. That's the hybrid Merlin that will be flying first with the normal reduction drive, and then after getting the benchmark data, we will convert that top pulley and remove that and insert the hybrid system, and then fly it on gas, and then fly it also on electric, and then fly it combined. But first bench test, and then we have the platform already finished, so we'll be flying the first parallel hybrid this year. Now, the next scaling up is what this can do. And you can see the different size, the different kilowatt motors that can go onto this. So we're circling back now to Brian, where he'll describe how to integrate the electric motor here.
Okay. This engine mount is divided into two sections. And this one carries the loads past the recuperator heat exchanger. This truss right here can be modified to tie the engine mounts into this structure and then also into a structure that will mount the motor above the gearbox about here. We'll take the isolators off here and put them on the actual mounts that hold the motor gearbox and the propeller, which now has been raised up to here. Just like with the reciprocating engines, we can operate with the motor engaged, perhaps 180 horsepower for takeoff, and then turn the motor off and use it to charge batteries during cruise. Also, another benefit of having the thrust line moved up with a structure here and a gear, we'll say a reduction drive, we now have an opportunity for a through hole so that we can run a standard hydraulically operated constant speed propeller. So we can basically run a constant speed propeller at a lower speed than this propeller operates at, perhaps in the sweet range, 2300 to 2600 RPM for low noise, and be able to use an off-the-shelf propeller governor and pitch control.
Well, we keep finding further benefits of this. One of them, by moving the power output higher, we gain more ground clearance of the propeller. By gaining more ground clearance, we can put bigger blades on and more blades and longer blades, which is not only more efficient, but we need that, especially the adjustable pitch, to soak up all that horsepower that we're now putting on with two power systems. And another benefit, and maybe you should talk about this, Brian, is that turbines love cold air. But they're not so great when you have a hot air on the ground and you want to get to altitude. And what we're doing, the main premise, or one of them with the parallel hybrid, is we're not carrying thousands of pounds of batteries. We're only carrying a minimum amount of batteries to assist in getting up in the air. But having that extra power to supplement the turbine means that we can get this turbine up to colder air where it can run more efficiently, and that'll be a major benefit in range extension.
Yes.
Was that clear enough?
That was clear, and maybe an additional benefit you might want to mention is that batteries don't care about density altitude. Perhaps there is degradation in propeller performance, but we do not have the degradation in, we'll call it engine performance, because electricity doesn't care what altitude it's at. So you'll have the full power available from the electric motor, whether you're flying sea level or out of Denver, Colorado.
What is the specific fuel consumption of this engine, and how does that compare to a reciprocating engine or other gas turbine engines, Brian?
I'll start by saying small turbines typically less efficient than piston engines. Now, this engine is different from many of the other turbines you see. It incorporates a heat exchanger here that takes heat from the exhaust and returns it to the air downstream of the compressor. And this thing is responsible for 15 or more % reduction in fuel flow. This engine, perhaps cruising at 10,000 feet, neglecting inlet ram, should burn about 7 gallons to 7.3 gallons per hour of jet fuel. A typical turbine of similar power would probably be up around maybe 11 to 12 gallons per hour.
Yeah, that's a
that's a 15 to 20% difference, which is huge when we're talking about the tyranny of distances. Not only that, but this can turn into a stealth mode when we get on target, and we can just turn it off and come in nearly silent with the electric motor.
Yes, and I'll even throw in another benefit. When you parallel hybrid something like this, you're giving yourself the extra power that you need to take off out of a short strip or some crazy runway someplace. When you get up to cruise, you're cruising now with a smaller gas turbine than you normally would have needed if you had to have that power solely from the turbine. So you're going to be running a smaller gas turbine at a higher power level, and when a gas turbine runs at a higher power level, it gets better fuel efficiency.
I'd like to continue a quick tour because on these programs, commercialization is quite a big factor. And I'd like to point out that we've been at this show here now 44 years, and we're in the center, air show center, prime real estate in the general aviation section, and we've got basically equivalent of 3 booths. So we're just gonna walk down here and have a quick panoramic of, we've got this hybrid Merlin. And I need to point out something special about this. It's be ready to fly in just about 2 weeks, but it's the first Starlink enabled light aircraft. And we've 3D printed a mount, and you can see that on the top, or you can see it from the bottom. I'm not sure, can you see that? So this is an active Wi-Fi now. It's really a truly mobile hotspot, and we've been using it all week for our phones and tablets. But we have another feature on this aircraft, because this will be hybrid, and if you show this, which everybody refers to as Bombay doors, because that's kind of what they are, that allows us to load and unload the battery packs. Remember, we're not, hybrid is only using the battery a little bit, like 5-10 minutes. So we're not carrying hundreds of pounds, we're carrying like 20-30 pounds, easy to load, easy to unload, and in case there's an incident, easy to eject. So we can offload the batteries should there be a catastrophic failure of the batteries and they're gone. There's another benefit that maybe you might mention there, Ben, of what else we can load in there?
Yeah, if we had to load supplies or some sort of a kinetic effect payload, we could do that easily using this system. Another thing about this particular aircraft is that it's set up to be a drone. By that I mean it can fly autonomously. It has all of the servos and all of the electronics to be able to fly on its own. One of the key features that we designed into this aircraft is the fuel system. In most light aircraft, the fuel system the fuel is distributed in more than one tank. So what we're doing with this one is we're no exception. We have tanks in either wing, but the way that we manage the fuel is through an all-automatic fuel system that allows us to draw fuel either from the left, right, both, but in addition to that, we can take the fuel and deliver it on a timer or a balance system. If you look in the cockpit here, let me get in the way here. We have a fuel management system that in this position is in the off position. Then we have left, right, both, and then we have timer, which means that the fuel will go between tanks left and right every 5 minutes, and balance. That system there is on a PIC type of controller, all burned into hardware to allow this to function. The lights tell us which tank is feeding, and these two lights tell us whether we're in manual mode or automatic mode. This entire cockpit, when manned, is a full electronic flight information system. It has synthetic vision. All of the radios, all of the navigation radios, GPS included, are there. Now, another feature of this is that because we have Wi-Fi streaming in and out, we can access this aircraft remotely using VPN. In other words, we can take this screen and bring it to our ground control station, not with a separate ground control station, but with a browser. So we'll be able to make a Zoom call to this particular aircraft and fly it that way. VPN is actually the way we're going to do it, but that means that this thing has a dedicated IP address which we can access. And as I'm thinking that this may be the first and only aircraft that will be able to be managed, controlled, and flown using Starlink.
Right, and that benefit in GPS denied theater. I'd like to mention, if you show here, we've already installed or prepared the mounts on 7 different servos. So this servo here, and I'll show you the servo if you bring the servo over, is the steering, because it's a steerable nose wheel. So not only does it steer the nose wheel on the ground, but it has the rudder for one axis of the flight. Now in the back, you won't be able to see them, but there's 2 conventional servos for pitch and roll that are normal for a 2-axis autopilot. And then we have a brake servo and a throttle servo. The throttle servo might be simplified with this electronic throttle, just like because this has a mechanical switch on the fuel board, but it's a microprocessor behind, so that can easily be controlled simply with a signal. And then there's another flap for the flap. So we have a 0 to 40 degrees with a 5-position flap up there. And we have this aircraft has a rocket propelled parachute. So we have a parachute that will bring the whole rocket down. It opens up in under 3 seconds and floats the whole craft down. And there's a servo to enable the parachute. And of course, then there's the Bombay doors, which can deliver humanitarian aids, blood canisters, type-specific blood, drop off the batteries, drop off other payloads, or kinetic devices. And that's on a servo as well to open and close those doors. Now there's a variation that we have in design to add more, because it's quite simple to increase our range because the fuel tanks are in the wing. We can triple the amount of fuel and simply add those fuel pump in each tank, and it's just simply a matter of selecting which fuel pump to turn on, and that's all you have to do for fuel management. It's very simplified, and we can do 4 times the range, and we already have 500 miles range on this.
I'd like to talk a little bit about the type of servo that we're using. So in a lot of aircraft that are both optionally piloted and autonomous, the servos are difficult to disconnect. So in a lot of cases, that's a problem. This particular servo is a linear actuator, but as you can see, the actual actuator free floats. The reason it free floats is because there's a split nut on the inside that grips the Acme screw to actuate it. So when we energize this servo, that's when it becomes a servo. Otherwise, it's just free floating. It also has what's called an LVDT in here, linear variable distance transformer, to give us the position of, in this case, this is where we're using this one for the rudder and for the nose wheel steering. We will know where the nose wheel steering is, whether a pilot is actuating the nose wheel steering or whether the software is.
So there's also an electric trim tab on here, but basically the key point of what Ben was saying was when there's a pilot on board, all axes are free. The pilot can control the aircraft. There's no friction or insignificant friction on all the servos, and that's a pretty big deal because anything above 55 pounds is very difficult to fly. So to test flying this type of UAS, very simplified with a person in it, and just monitoring. It doesn't have to fly it. Someone on the ground can be flying it, or autonomous, completely remote, even beyond line of sight. But the pilot is in there, so he is perfectly legal in most aerospace in the United States, and he can take over the controls and if he needs to. I'd like to put a plug in for what we think is our optimum UAS, and that would be this airplane, which is the Leopard, which stands for long endurance, because we can put all that fuel in there, an 1,800 mile one range. Optionally piloted because you can put a person in there, or easily carries 300 pounds, so there's a huge payload. Trittable because these are low cost and they can go one way. We don't care if they come back, and it takes if it's shot down with $1 million missile, that's a win for us. We can send 20 of these out and they shoot down 10. That's $10 million of missiles that opposition no longer has. And then reconnaissance, because you can have sensors on here. we have also retractable gimbal, and other various sensors are available, and drone. So the Leopard also has a very large commercial market because the private pilots moving down from their more complicated Bonanzas and Cessnas, because they're getting old and they're expensive to fly and expensive to maintain, can buy an aircraft like this on the retail market for about $75,000. They can go 150 miles an hour, they can have retract, they can have adjustable prop, and they can have an affordable aircraft. So we're looking forward to a large military and commercial market with that. And we're the experts in that. We've been doing this for decades and built over 1,000 aircraft. So these are right in our wheelhouse on what to make. And then we just have to upgrade the game here by incorporating that hybrid engine in it. So we can take off with more weight and more fuel because we have that extra electric power, and then we're more efficient at altitude.
I'd like to talk a little bit about the patent portfolio that's part of the hybrid aerospace. So we have a total of 7 patents that have been issued. We do have several that are pending, but we don't really talk about the patents that are pending because that's not IP that we own. But we do have the patent for an electric a hybrid type of design that includes battery pods that have powered propellers on them and can be jettisoned. We have that patent. We have, of course, 2 patents for a parallel hybrid aircraft engine. We have patents for propellers that are near the ailerons on either side to de-spin an aircraft in the event of a loss of control. We also have patents for propellers distributed all over an aircraft to control it in the event of a slow flight incident, and then particularly for the situations that I just described where there's a potential loss of control. And that's kind of how Aeromarine operates. It's not just a company with in this case here just patents, but there's actual hardware. There's customers purchasing aircraft, engines, and technology from us, and therefore there's a lot more going on here than meets the eye.
Right. Well, just a quick glance at these slides, because we're very close now. We have designed the electric propulsion system. It's not a hybrid, it's pure electric, and electric actually works very well on a very clean and a low energy aircraft like an ultralight aircraft or a motor glider. And we happen to have an ultralight and motor glider aircraft in our portfolio. We're building the airframe now to be flying this this year, and we already have orders for this. And the brand name is Electrolight, and that'll fly 1 hour on electric. And I'll show you that. If you look at this airplane here, on the left is the motor glider wing, and that is the Electrolight. This one is gas powered, but it'll be gas and electric, so customers can choose 1 hour of endurance and nice, clean, quiet, safe electric flight, or conventional 2-stroke gas engine and 3 hours of flying. But the mission of many of these people are just the pilots just want to get up and fly for an hour, dawn patrol, evening flight, or get up and soar with that long wing. We didn't have room in our booth to put the ultralight in with the short wing, so we simply just put the wing on this aircraft because they're interchangeable. You can convert this airplane in a half hour to an ultralight with a short wing or a motor glider with a long wing. And it gets even better because for decades we've been selling these floats. And these floats are ultralight floats. You can pick it up with 2 fingers. It's a 30-pound float, and you put 2 of these on this aircraft or a new ultralight that we're introducing this year, because float flying expands the universe, expands our flying. And real quickly, this is a pure ultralight, which means it's a Part 103, no license, no medical, and a folding wing, which folds in about 4 minutes. So this airplane can be towed on a trailer, and you don't need an expensive hangar, and it's easily deployable. It's more of a recreational vehicle, but it saves a lot of hangar space and a lot of expense. And it's a $32,000 finished aircraft that with a parachute built in and a moving map EFIS and electric flaps. So it's quite a nice aircraft, especially for that price. So take a quick look. Our booth is quite a bit of stuff here in our booth this year, as usual. Well, that's for now. I'm signing this video off. We've got a little interference with the air show, but a lot of commercialization going on here at the world's biggest air show, Oshkosh 2024. Chip Erwin, Aeromarine.
Here's the setup, the ESC, one single battery connected to my computer to this system here. I got to work on the ACT deck, which is how it starts. But if I put on the brakes, which is this button right here, it uses real heavy braking. And then this is, and that noise you hear is the Hall effect sensors. I think it might just be this motor. It may be a little bit off. It's running in the wrong direction right now, but I can fix that.